Hello, everybody. This is Dr. White, and we are recording solutions for the Section 5.3 DA on basic hypothesis testing. I'm going to share the screen. We're going to take a look at those solutions. Okay, let's go find them. Here we are. So those solutions are posted in the common folder on the RStudio server under Old DAs worked by Dr. White. The key to this DA really is the last section of the 5.3 slides, steps of hypothesis testing. So that was the section where we took up an example investigating what proportion of adults in the US favor the death penalty by using a data set, the GSS 2012 data set, looking at the Capun variable in it. Capun was whether or not you favor or oppose capital punishment, and 1,183 out of 1,824 favored capital punishment. And was this considered strong evidence that a majority of all US adults would favor the death penalty if you could have asked all of them back in 2012? And so that example was taken step by step through the 4 major steps of a test of hypothesis. If you look carefully at those slides, you can use that as a model for pretty much all of your problems in this DA. So first one, unexpected expense. That's actually a bad title, and I think I should change it. It's actually, I should call it maybe like, I don't know, alcohol in Wisconsin or something. But here's the scenario. The state of Wisconsin would like us to understand the fraction of its adult residents that consumed alcohol in the last year. Specifically, what they want to know is the rate in Wisconsin, the percent of all people in Wisconsin who drink alcohol, is it different from the national rate of 70%? So somehow we know from other data or some big study that nationally 70% of adults drink alcohol. Is Wisconsin the same or different? To help answer this question, they conduct a random sample of 852 residents, and they ask them about their alcohol consumption. Do you drink alcohol? Yes or no? So remember, in the 4 steps for hypothesis testing, the first step is to prepare. And the prepare step has these 4 sub-steps. Identify the parameter of interest, list the null and alternative hypotheses, identify what significance level you want to work with for this problem. That's your cutoff for your p-value. You know, if your p-value is less than the alpha, you'll reject the null. Bigger than alpha, you won't. And lastly, kind of get yourself started by at least identifying what the sample proportion is and the sample size. And so here, we're addressing the first thing, identifying the population parameter. Well, that's just the proportion of all adult residents in Wisconsin that have consumed alcohol last year. Next sub-step was writing the null and alternative hypotheses. And I would write it like this. You know, in this section, you're told yet again that the null hypothesis is always going to have to claim that the population proportion is a specific value. So what should you claim in this case? Well, we've got this figure of 70% for the nation. We're wondering if Wisconsin is above that rate or below it. So why not let the null say that P is at that rate for Wisconsin? And then the alternative can disagree. It can be saying that Wisconsin is either higher than that or lower than that. Okay. That's all we got for this scenario. Let's check this next scenario, married at 25. So you've got some previous study that suggests that 25% of 25-year-olds have gotten married by that time in their life. and you doubt that study for some reason. And so you decide to collect your own sample and do a hypothesis test to see, like, does it really look plausible that 25% of the population of 25-year-olds have gotten married by now? Let's see. Well, looks like you take a random sample of 776 25-year-olds, and you find that 24% of that sample are married. And say you get on to the part of the prepare step where you have to set up a hypothesis test. So, like, you already know that the P you're interested in is the proportion of all 25-year-olds that have gotten married. And your friend thinks that the null hypothesis should say that P hat is 0.25 and the alternative should disagree. Well, she's right about the null having to put forth a particular value. But she's wrong about that it should put forth that the sample proportion is a particular value. After all, nobody argues about the sample proportion because they know it. It's just like you don't make a confidence interval for a sample proportion because you already know it. What you don't know is the population proportion. What you want to know is whether it's 0.25 or not. And so here's how you should do your null and alternative. It should be about P, not P hat. Okay. Next one, in this scenario, we're going to take it all the way through all the 4 steps. So in the scenario, 400 students are randomly sampled from a large university. 289 of them said that they did not get enough sleep. So from that scenario, you can tell what people were interested in. It looks like they wanted to know about P, the proportion of all students at the big university who do not get enough sleep. And they've got a sample to try to estimate that. All right, and notice that you're going to use a cutoff value of 0.01 instead of the usual value of 0.05. That'll come later. Okay, prep step. Do all the sub-steps in the prep step, all 4 of them. So first off, identify the population proportion in words. Great. Let P be the proportion of students at the university who do not get enough sleep. Hypotheses. The null hypothesis is going to have to say that the unknown population proportion equals some value. What value should it propose? Well, it's just like that majority-minority question about the death penalty. When you got a majority-minority question, like you're wondering if the data provides strong evidence that a majority of people do something, or does the data provide strong evidence that a minority of people do something, then it's a good idea to let the null hypothesis say that the unknown population proportion is right at the boundary between majority and minority, 0.50. So we'll go that way with our problem. And so the null saying that P is 0.50 is saying that out there at that university, neither a majority nor a minority of the population gets enough sleep. The alternative disagrees. Now you need to note down your sample size. That's 400. I'm going to call it N. Maybe I can use that later. And you need to note down the sample proportion, 289 over 400. And I'll print that out to see what it is. And look at that. It's 72.25%. You know, if the null is right, and you know, when you do a test of hypothesis, you temporarily assume the null is right. And you wonder, like, how likely is it to get data like what we got if the null is right? You know? So you're thinking here, you know, if the null is right, then half population doesn't get enough sleep. So when you take your sample of 400 people, you'd be expecting about half of that sample not to get enough sleep. Instead, like 72% didn't get enough sleep. That seems like a lot more than what the null hypothesis would be expecting to happen. So this already looks a little alarming for the null, but you need to get more precise and more scientific about it to see if like the 72.25% is so far away that it couldn't just reasonably be chance variation in the sampling process. So let's see. Next up is the check step. You're going to be using the sample proportion, which you're assuming is approximately the normal distribution. And out of that, you're going to construct this test statistic Z, the Z-score. And that you're assuming has approximately the standard normal distribution. So for all that to work, for the p-hat to have approximately the normal distribution, remember your sample size needs to be big enough. How big? So big that there's at least 10 of each of the two possible answers in your sample. The no, I don't get enough sleep, the yes, I do. The no, I don't get enough sleep is the successes this time, because we're counting that up. That was 289, so that's at least 10. The number of people in the sample who did get enough sleep would be 400 minus 289. That's 111. That's also at least 10. So we totally have a big enough sample here. So when we go and do things like make confidence intervals, get those p-values, using the p-norms you see, we're going to be okay because our variables do have the normal distribution that those computations assume they have. Next up is the calculate step. So like over here, that's this step here. It's got 3 sub-steps. Get the standard error, get the test statistic, get the p-value. Don't forget, when you get the standard error in a hypothesis test, you are still in this mode of assuming that the null hypothesis is true so that you can figure out how likely it is to get the kind of results that you would get, that you got if the null is true. So since you're assuming that the null is true, you don't have to guess at the standard error for p-hat. You don't have to stick a p-hat right in here where you really need the p in the actual formula for standard error. You can stick what the null hypothesis thinks p is. So we're going to be sticking a 0.50, right? I mean, in this example, we're sticking a 0.50 right there because that's the null hypothesis in this example. So back over here, it's the same thing. Our p-naught was set to be 0.5 because of being the majority-minority question. So we can go grab our standard error, and it turns out to be 0.025, about 2.5%. Stop and think about that for a moment. Null's expecting 50%, give or take some for, for chance error in the sampling process. You got 72.25%. That's a lot of 2.5% above 50%. So it seems already that this data is really bad news for the null hypothesis. But we can be more precise by finding exactly how many standard errors the p-hat is above the null value. We just find the z-score. And here I am printing it out, it's 8.9. So that 72.25%, it looked intuitively like a lot more than the 50%. And yes, it was really a lot more. 8.9 standard errors above what the null was expecting. Highly unusual to get such a thing if the null is right. I think we're more likely to be struck by an asteroid in the next 10 years than to get a z-score that high if the null is right. Well, what is the chance of getting a z-score at least that high? That's the p-value. If the null is right, what's the chance of getting a z-score that is that far away? Well, or further. So you look for the chance of getting outside the region from minus 8.9 to 8.9. And as you can see here, it's practically nothing. 0. More specifically, it's about 5.58 times 10 to the minus 19. Great. That's the 3 sub-steps of the calculate step. The standard error, the z-statistic, the p-value. Now we need to make some conclusions based off of this. Before we can make a final conclusion, we need to decide what to do with this null hypothesis. And so you need to compare, and looking at the slides, you need to compare the p-value to the level of significance. And you're going to reject the null if the p is less than the alpha, not reject it if it's more. So I look at that p-value, and using my knowledge about scientific notation, I see that it really is about 5.58 divided by 10 to the 19th. That is a super small number. It is certainly less than that level of significance 0.01 that we set up for ourselves. So we are totally rejecting the null hypothesis. But there is one more thing to do, and not enough people did it. As I went through looking at the DA, not enough people did it. That last thing is to write a simple conclusion that states in the context of the problem how much evidence the data provide against the null, or you could say for one of the directions of the alternative. And let's see how we do it this time. Well, so we got a p-hat that was 72%, and that's making it really look like p must be bigger than 0.5. It's really looking like we got a majority of people at the university that don't get enough sleep. So we'll just write that up. We conclude that the data provides strong evidence that a majority of students at the university do not get enough sleep. When you reject the null, you've got strong evidence for one of the directions of the alternative. So that's all 4 steps of hypothesis testing. We're going to be repeating those steps ad nauseum for the whole rest of the semester, the whole next 2 weeks. So the last thing is just 5 little questions where I give you 2 scenarios, and and I ask you which scenario makes a certain quantity bigger. And some of these things are just reviews of previous material. Like standard error of the sample proportion. Is it bigger for this smaller sample size or this bigger sample size? But we know that when you increase the sample size, you're making the n bigger in the fraction for the standard error. You're making the standard error smaller. So I'm asked which scenario makes it bigger. So I'm going to say it's bigger in scenario 1, where the sample size is smaller. Next up, margin of error of the confidence interval. One scenario, you're making a 90% interval. The other scenario, you're making an 80% interval. Well, the more confidence you want, the bigger the z-star number has to be, therefore the bigger the margin of error. So I would say it's scenario 1, that's where the margin of error is going to be larger. So that's still review from previous sections, based on confidence intervals. Now here's something new. Consider the p-value that's based on a z-statistic of 2.5. And suppose that that statistic of 2.5 came out of some calculations with your sample. In scenario 1, the sample was size 500, and in scenario 2, the sample was 1,000. Of course, you would need to know more than just the sample size to get your z-statistic. You would have to know the sample proportion, and you would also have to know the null value, what the null hypothesis thought p was. But suppose that in each of these different situations, you got 2.5 in both of them for your test statistic. How about the p-value? Which scenario would make it bigger? Well, think about how you calculate p-values. For example, up here. It's the chance of getting outside the range from minus z to z on the standard normal curve. Whoa, the only thing that probability depends on is the z statistic. It doesn't depend on the sample size directly. It only depends on the z statistic, and that was 2.5 in both scenarios. So I'm going to have to say that it's the same in both scenarios. The p-value is the same in both scenarios. I can even calculate what it is. It's about 1.2%. Now for the last two, parts D and E, you're going to need to head back to see the definitions for type 1 error and type 2 error. So that's back on slide 41, where we first defined these concepts. Remember, a type 1 error is something that happens if the null hypothesis is true and you incorrectly rejected it. Type 2 error is something that happens if the null hypothesis is false and you incorrectly failed to reject it. Okay, so let's see here, part D. Quantity we're interested in is the probability of making a type 2 error when the alternative hypothesis is true. And the significance level is either scenario 1, 0.05, scenario 2, 0.18. So like in scenario 1, you're going to reject the null if p-value is less than 0.05. Scenario 2, you're going to reject the null if the p-value is less than 0.10. So let's think this through. By definition, a type 2 error occurs when the null was false, but you don't reject it. Now, when the null is false, the alternative is true. So you can say to yourself, a type 2 error occurs when the alternative is true, but you fail to reject that false null hypothesis. Now, when do you reject a null hypothesis? You reject it when the p-value is smaller than the level of significance. Now think about this. The smaller the level of significance, the less likely it will be to get a p-value that's smaller than it. You know? Think about 2 feet versus 10 feet. It's easier to be shorter than 10 feet than it is to be shorter than 2 feet. Pretty much every human being in the world is shorter than 10 feet. No adult human being is shorter than 2 feet. Same for p-values. It's easier to get a p-value that's less than 0.1 than it is to get a p-value that's less than 0.05. The smaller the level of significance, the less likely it is to get a p-value smaller than it. Therefore, the less likely it will be that you'll reject the null. Therefore, the more likely it will be that you will fail to reject the null. But that puts you in type 2 error land. So the smaller the level of significance, the more likely you will be to make a type 2 error. So I should go with scenario 1 because that has that smaller level of significance. In my mind, that's the most difficult problem in the DA, because you really have to think carefully with the definition of type 2 error, and you have to think about how a hypothesis test works. Now, part E. Okay, the quantity you're interested in is the probability of making a type 1 error when the alternative hypothesis is true. 2 scenarios are the sample size is 100, sample size is 400. Well, this one's a little bit easier. How do you make a type 1 error? Well, null has to be true, and you reject the null. Well, here, the alternative is true. In both of these scenarios, the alternative is true. So the null is false. So you cannot make a type 1 error here. You cannot incorrectly reject the null when the null is false. So no type 1 error is possible. Therefore, under either scenario, you cannot make a type 1 error. You could say 0% chance of making a type 1 error in either scenario. So I guess I'm going to have to say that the probability is the same under both scenarios. It's 0. I think there was one person who got the entire DA correct, and there were several people who got these last two correct and explained their reasoning as well. That was impressive. It was a lightly graded DA. As long as you tried and got a few, you got a 10. But I was real impressed when people went and just got almost everything. That stands you well for the last part of this course. Okay, that's the DA. Would there be any questions on it before we leave it? Okay, I'm going to stop sharing and stop the recording.